Good morning. Today's lecture is going to be a short one. I'll quickly wrap up our discussion about optoelectronics, then tell you a little bit about the final exam, and then answer any questions you might have about anything in the class. So last time we discussed the fact that all kinds of optoelectronic devices could be made up of a p-n junction under illumination, simply depending on the quadrant in which you operate the thing. If you operate the thing in quadrant 1, you get forward bias devices under forward bias devices, and under those conditions, the injected electron hole pairs can recombine, especially if it's a direct bandgap semiconductor, and emit light as in a light emitting diode, or if the light comes out in phase rather than in random phase, you get what's called a laser. Nothing happens in quadrant 2. If you operate in quadrant 3, you get what's called a photodiode or photodetector, and that's what we'll start off today. And then finally, in quadrant 4, the diode actually acts as a battery, as a power source, where it converts the incoming radiation into useful electrical output. We discussed that last time. So today we'll discuss photodiodes first, and then briefly talk about LEDs. And I'll just quickly mention how lasers operate, but you'll not be responsible for that in the exams. So the key physics is illustrated over here. If you have, say, a reverse bias p-n junction with a certain depletion with W, and I shine photons on it with an energy h nu greater than the band gap so that I can absorb the photons, create electron hole pairs, electrons and holes within diffusion lengths, L sub n on this side and L sub p on this side, the minority carriers, can diffuse to the edge of the depletion region and be swept across this reverse bias junction. In reverse bias, of course, we know that's my p side, that's my n side. So if I create minority carrier electrons in the p side within a diffusion length ln, they can diffuse to the edge of the depletion region and be swept across. Similarly, minority carrier holes on the n side within a diffusion length of LP can diffuse and be swept across. And that's what I'm seeing over here. So you get additional leakage current. I'm increasing the supply of minority carriers in the reverse bias diode. And I'm basically increasing the supply over and above the black body radiation, which gives you G thermal. Okay, so now I only have G thermal, G optical is 0. That's the regular IV. But then with increasing photon flux, I get more leakage current. And obviously a measure of the leakage current is a measure of the photon intensity, the photon flux. So that additional current gives rise to this optical current on top of the regular IV of the diode, as shown over here. You can come up with an expression for the optically generated current as the generation rate per unit volume G optical. So that's number of electron hole pairs per centimeter cubed per second, times the volume. The volume is the collection length, the depletion width plus diffusion lengths on both sides, times the cross-sectional area A. So that then gives you the number of particles, number of electrons holes that are collected per second. So GOP gives you the number per centimeter cubed per second, times the volume gives you number per second. But then to get the current, you have to multiply that by the charge of the electron, which is minus Q, which is what you get over here, okay? Now that's your master equation. You can then solve that to get what's called the open circuit voltage by simply setting the current to 0 and solving for V, which works out to this. Or alternatively, you can get the short circuit current by setting the voltage V equal to 0, in which case the first term drops out because you get e to the power 0, which is 1 minus 1. And I'm left with the final term, which is your short circuit current. So the short circuit current would be these currents, while the open circuit voltage in the solar cell would be these voltages, okay? Yeah, so I've already talked about this. So let's jump towards photodiodes or photodetectors, which, as I've told you, form a key component of optical fiber optic communication, which forms the bulk of the long distance high volume communication in the world today, where you have lasers modulating the electrical signal through digital bits, ones and zeros, which pass through these long fibers, hundreds or thousands of miles long, under oceans and things like that with periodic repeaters. And then at the other end, these optical signals are converted back into electrical signals using a photodiode photodetector. You electrically shape the signal, and then you finally have a D to A converter to convert the original analog signal back into an analog output. Okay, so a little bit more detail about the physics of the photodiodes. So this shows one of the most basic forms of a photodiode, a so-called PIN diode. I standing for a intrinsic region, intrinsic meaning very low doping. Now, generally, it's impossible to get zero doping, so it'll be slightly p-type, in which case it's called a p-pi n diode, or slightly n-type, and those are known as p-nu n diodes. Okay, so pi and nu are basically lightly doped, almost intrinsic. Now, the issue is if I have an intrinsic doping such as this, if I flip the structure and I draw the band diagram, what you end up getting is in the P region, you have this. Then in the long I region, you get a band bending like this, and then you have N, where in this I region, these band edges will actually be linear. In a regular PN junction, we have said that although we kind of draw them kind of linear, but if it's a step junction, it's really a parabolic shape joining smoothly to another parabolic shape. So it's not really linear. It's two parabolas which join smoothly. Approximately looks linear. But in the case of a PIN diode, it's exactly linear. Why? Well, if I have doping over here, I have negative charges in the acceptor ions that are exposed and positive donor ions that are exposed. And then you'll have field lines extending from the pluses to the minuses. And there's no charges in the, no dopant charges in the I region. And therefore the field is going to be constant within the I region, meaning that the slope of the band edge is going to be constant. Now, in such a scenario, if I now shine photons which are absorbed, HD greater than the band gap, I'll create electrons in the P side, holes on the N side, and if they diffuse towards this I region, they'll be swept right across. Similarly, any electron hole pairs that are generated in the I region will be swept across, okay? So that's the nice thing about a PIN photodiode. You can determine the volume within which carriers will be collected by simply determining what the length of this I region would be. That's something that you can design in the diode. You're not depending on the width of the depletion region per se, kind of determine the volume over which the carriers will be collected. And that's going to be important because that's what will give you high sensitivity. What does sensitivity mean? Sensitivity means how much electrical output I get as a function of the light flux. And obviously you'd want as high of a sensitivity as possible. And then that tells you immediately that I want the I region to be as thick as possible, right? Because if it's very, very thick, when I shine light through it, I'm guaranteed that all of that will be absorbed within the I region, and I'll get the maximum electrical output possible, okay? Now in the simple version, the maximum we can get is, of course, one photon will give you one electron hole pair, right? You can't do any better than that, okay? But by making the I region wide enough, you guarantee that at least every photon will be absorbed, hopefully within the I region, and you'll get electrical current corresponding to that, okay? In a second, I'll tell you how you can improve on the sensitivity, okay? But before I do, unfortunately, as you increase the sensitivity by making this I region wider and wider and wider, the diode becomes slower and slower and slower, okay? Why? Well, just think about it. If I'm creating an electron that has to go this way, and the hole that's created has to go this way. If I make this region wider and wider and wider, the transit time across the I region is going to be longer and longer and longer, and therefore the speed of the diode, photodiode, will become smaller, right? The transit time is longer, and therefore it becomes a slower device, okay? The speed and the sensitivity jointly are often described in a diode or many semiconductor devices as the so-called gain bandwidth product. The bandwidth is the highest frequency of light, for example, which can be modulated on and off, and the photodiode can respond to that, okay? So if that's my light output, you want the electrical output to kind of follow that also, right? Now, if I vary the light output very, very fast, because if I have a long eye region where the transit times are long enough, the electrical output may not be able to track the light modulation. I might get something like this, okay? So that's bad. So the highest frequency of light modulation, which can still be detected as a modulated electrical output, determines the so-called bandwidth, okay? The gain is how much electrical output I get as a function of the light input, which is determined by the sensitivity, okay? Now, in the case of a PIN diode, the maximum possible gain, or the so-called quantum efficiency, is 1, because as I told you, 1 photon absorption gives you 1 electron hole pair. Can't possibly do better than that. And in fact, it'll be, in general, slightly less than that, okay? Now, along with this gain bandwidth product for these photodiodes, another important electrical metric is the so-called signal to noise ratio, okay? So the signal is electrical output that I'm getting, okay? But unfortunately, on top of this electrical output, suppose I'm shining a steady light output, okay? The electrical output, instead of being a steady signal, will have some random noise on top of that, okay? And there's multiple reasons behind that. One of the important ones being so-called short noise. What is short noise? Well, you know, in electrical engineering, we often pretend that this electrical current is a smooth, continuous flow of a charged liquid, right? But really, it's got a granular structure to it, right? It's made up of electrons, which are discrete, and holes, which are also discrete. So the output terminals, if I have especially low light intensities, you may get statistical fluctuations of the number of electrons and the holes that come out at the terminal. So the number of holes that come out and the number of electrons that come out at the two ends will, the holes come out at this end and the electrons at the other end. That will have a statistical fluctuation. Now, if the numbers of those electrons and holes are large, that statistical fluctuation on a fractional basis, of course, is going to be small. But in these photodiodes, they're typically sensing very, very low light intensities in many cases. And under those conditions, this random electrical noise, because of the discrete nature of the electrons and holes, gives rise to what's called short noise, okay? And there can also be statistical variations of this electron hole generation process. There's multiple sources of noise. There's another source of noise called Johnson noise. We won't get into the physics of the noise. It turns out the mathematics of noise physics is extremely complicated. You have to use, you know, very, very deep theories of stochastic processes, Markov processes. You can have a whole semester course on noise theory, in fact. All right, so I've told you that a PIN diode is a very simple device and it's used, but it suffers from the problem that it does not have gain, meaning that one photon in, you get a maximum of 1 electron hole pair out, okay? That problem is solved in what's known as the Avalanche Photodiode, okay? Or an APD. An Avalanche Photodiode, or APD, Avalanche Photodiode, or APD, is a structure where you can get gain, okay? In other words, you can get electron hole pairs which are more than the number of photons that are absorbed. How is that possible? Well, it's a more complicated structure where you have a low band gap semiconductor, in this case, say InGaAs, Indium gallium arsenide, which is my so-called absorption region. So when I shine light into the structure, most of the light gets absorbed in the low band gap semiconductor. So if I was to draw the band diagram as a function of depth, I'd have low band gap in the absorption region, then a higher band gap in the so-called charge separation region, and then finally, in the charge separation region, and then finally in this multiplication region, I'll have a larger band gap, okay? Now in general, of course, you don't have sharp transitions like that because that can give rise to problems. You grade the heterostructure and you have smooth variations of the band gap in these heterostructures, all right? So then I'm shining photons on it. In this band diagram, mind you, I'm flipping the usual way I draw the band diagram. So energy points this way. So EC might be over here, EV is over here. I'm trying to correspond the band diagram to the structure on the right-hand side, okay? So when I'm shining photons on this, I'll be absorbing them in this absorption layer, okay? So I have a high absorption rate as shown in this, okay? Now, the photon energies are such that they are lower than the band gap in the charge layer and the multiplication layer. So they cannot be absorbed within these two systems. All right. So what's the role of that? The role is you design this PIN diode structure where these absorbed photocarriers within this high electric field region. Okay. The electric fields are high in this so-called multiplication region. These injected electron hole pairs undergo impact ionization and carrier multiplication in the multiplication region, and that's shown on this right-hand side. Okay, so in other words, if I was to draw the band diagram of this PIN structure, so I have a low band gap absorption region, then the charge separation region, and then a larger band gap multiplication region. I create electron hole pairs. The electrons travel this way. The holes would like to travel this way. But what you do here is these electrons that are traveling this way undergo acceleration in this multiplication region. They become hot electrons. And as in the impact ionization process of a PN junction diode, this hot electron can impact ionize, create a secondary electron hole pair. Of course, in the process, it cools down. The secondary electron hole pair, the hole goes this way. This secondary electron and the primary electron accelerate this way. They gain more energy, and then you get a second generation electron hole pair, and so on and so forth. So if you look back at your notes about how avalanche breakdown or impact ionization process happens in a reverse bias PN junction, that's what I exploit in the multiplication region. Okay, so the punchline is one photon absorbed can ultimately give you many electron hole pairs, depending on how many impact ionization processes are going on. Okay, and by doing so, you can have a gain which is much, much greater than one, depending on this avalanche multiplication ratio. All right. So this makes it a very useful device because now you can have both high sensitivity as well as high speed if you design things properly. Now, it turns out there's a lot of physics that I've not covered in this also. This impact ionization process is a somewhat random statistical process, as I mentioned. Because it's random and statistical, that increases the noise in APD type structures unless I'm careful. Okay, how do I make the noise low? You can make the noise lower by making this impact ionization process more deterministic, less random. Okay, and the way that's done is by very careful choice of the materials, where I have a system where I might only get impact ionization due to electron multiplication, say. Okay, and I don't have a lot of impact ionization due to hot holes. And that's easy to do generally because we've seen again and again that electron mobilities tend to be higher than hole mobilities. Okay, so by making sure that it's only the electrons which undergo impact ionization again and again, and not the holes, you can minimize the noise. You can get rid of it completely, but that's one way of minimizing the noise. Okay, because I'm making this impact ionization process slightly more deterministic, slightly less random. Okay, so this APD type structure is one of the most common structures that you have in industrial use today. Now, there's other tricks that people play in order to improve the gain bandwidth product, meaning ways by which you can get both high sensitivity and speed. Okay, the issue once again is if you look at this structure on the top left-hand corner, you have a PIN diode or a PN diode, maybe with heterostructure, so that I get APD and so on and so forth. And in this system, I shine photons from the top, say, I absorb them, and maybe I multiply them through impact ionization, and these carriers are then collected at the two ends, the two electrodes. All right. Now, of course, you have to make sure that the top surface is not completely covered by metal, because then that would block the light. So you have a ring type electrode structure as shown over here. Now the bottom doesn't matter because you can have metal contact wherever. It doesn't really matter much. The blocking of the light on the top, the issue is very similar to what we talked about in the context of solar cells. All right. But anyway, if you look at this basic geometry that we've been talking about, the basic problem is we have this inherent trade-off between sensitivity and speed For high sensitivity, you need this absorption region to be wide, but then that increases the transit time and messes up your speed, okay? On the other hand, to get high speed, you need this volume, this thickness to be small, so that the carriers have a shorter distance to transit, but then that hurts your sensitivity, okay? So the issue is, how can you have your cake and eat it too? Well, one geometry is a so-called waveguide structure, shown on the top right, okay? So here, you decouple the direction of light absorption. So you now shoot the light in this direction at the edges of the so-called waveguide photodiode, but then you collect the carriers in the orthogonal direction, all right? By doing so, you kind of, you can make this thickness as short as needed to have the high speed that you want. But at the same time, I can make this waveguide as long as you need to absorb all the light, okay? And that's one way by which you can get high sensitivity and high speed at the same time, high gain bandwidth product. And furthermore, you can make this thing in an APD type structure so that they get an even higher gain. Now, the challenge, however, is somewhat of a technological problem, because remember that this structure, although on this PowerPoint looks nice and big, in reality is going to be a tiny cross-sectional device. And very often the issue becomes, and you have this optical fiber that comes in, you have to mate that to this tiny side of the waveguide APD type structure, okay? And if you don't mate that properly, there can be losses at the junction of the optical fiber, that's my optical fiber say, through which my photons are coming in that I'd hope to absorb and convert into an electrical output. So mating this optical fiber nicely so that you don't have light losses at this edge are an issue. Another interesting structure that has been proposed, not used very commonly, however, but it's very interesting physics, is a so-called resonant cavity photodiode structure. So in this, what you do is you have a thin absorption region so that you get high speed. These electrons and holes don't have a long distance to travel, but normally that would then mess up your sensitivity. So to take care of that, what they do is you embed this photodiode cavity type structure in a lower mirror, that's a mirror, and a partially reflecting upper mirror, okay? It can be a totally reflecting mirror because you want the photons to go through that, okay? Now these mirrors are a special type of mirror. They're made up of thin layers of two different dielectrics or two different semiconductors with different refractive indices. Those are known as Bragg mirrors, okay? After a physicist, Bragg. I won't go into the physics of that, but basically, if you have a periodic structure of refractive indices, by designing the thicknesses of these layers and the corresponding refractive indices, you can adjust what's called the optical length. The optical length is a product of the refractive index times the physical length, and that gives you the optical path length, okay? And what you do is, by carefully choosing these refractive indices and the thicknesses of these layers in this Bragg mirror, you can make sure that when light shines through, over here you'll have destructive interference and the light bounces back, okay? So the idea in a resonant cavity photodiode is, instead of making a single pass of the photons through this thin absorption region, the photon bounces back and forth, okay? And you give the photon a greater chance of getting absorbed and creating electron-hole pairs, okay? Very cute idea. The problem, however, is this resonance condition happens at specific wavelengths, okay? Because clearly you can see that you'll not get constructive destructive interference unless this is matched nicely to the wavelength of the photon, okay? So that in some cases can be a problem. So it's not been used that commonly. The APD type structure in a waveguide geometry is used. So that concludes our discussion about photodiodes. Our final device is a light source. So this is a light emitting diode, or a cousin of that is the laser. So here, I'm not shining light on it. Instead, I make a PN junction diode and I forward bias the thing, put it in quadrant 1. We know that if I have a forward biased PN junction, I inject electrons, so that's my P and that's N. I inject electrons over this reduced barrier, okay? Inject holes over the reduced barrier. These electrons and holes can then recombine. And if it's a direct band gap semiconductor, I plot E as a function of K, they can recombine and give up photons of light corresponding to the band gap of the semiconductor. So I can choose appropriate band gaps. I can get different colors of light coming out of it. All right. Now, silicon, unfortunately, as I've told you, is not a direct band gap semiconductor. Silicon conduction minimum is not at K equal to 0, but some non-zero K. So silicon is a no-no for making an LED or a laser. People have been trying forever. And if you get into the field and if you somehow manage to make a high efficiency LED or laser out of silicon, it'll be both rich and famous, okay? And in fact, you might win a Nobel Prize in physics. It's such an important topic because if you could get light sources out of silicon, good light sources, that really would be a dramatic change of the technology, because then you wouldn't need compound semiconductors, gallium arsenide at all. You can make use of cheap silicon-based optoelectronic devices. Now, there have been some progress made. You know, there are some reports of lasers made in silicon, so-called Raman lasers, but very, very inefficient. So it's really, you know, just for bragging rights, it's not really a useful device. All right, so the physics of the LED, like I said, it's very, very straightforward. It's just a forward bias p-n junction. You gotta make sure that you choose a semiconductor which is direct band gap, and therefore you get photons with color equal to the band gap. So one useful relationship that I mentioned in chapter 1 is the wavelength of light in microns equals 1.24 divided by the band gap in electron volts. Okay, so if I look at the visible part of the wavelength, that's obviously the most useful part of the light emitting diode. Blue light has a wavelength of 0.4 microns, while red has a wavelength of 0.8 microns. Okay, so plugging it in over here, for blue, you need 1.24 divided by 0.4, so that's roughly 3 eV, okay? But for this, you need roughly 1.5 eV or so, approximately, right? Yeah, roughly 1.5 eV. Now, unfortunately, gallium arsenide by itself has a band gap which is slightly lower than that. It's 1.43 eV. So if you make a light emitting diode out of gallium arsenide, you don't get even red light out of it. You get infrared, which is useless as a visible light emitting diode, but perfectly okay for your TV remote control. So in that, you really have a laser made out of gallium arsenide emitting in the laser, maybe an LED, depending on the product. So that, you know, when you point it at the TV screen, the TV has a photodiode which will convert these infrared pulses coming out of the remote control, and that's how you remotely control the TV, or any remote control is like that. Okay. Now, for those applications, you obviously don't need visible light output. Instead, that would be kind of annoying. On the other hand, for most LED applications, you need visible light output. Silicon, once again, is not useful in that context. Okay. Now, so because gallium arsenide itself was not good enough, people needed to increase the band gap of this alloy, and one way to do that is to increase the phosphorus composition in an alloy and make gallium arsenide phosphide. Okay, so the band gap of gallium phosphide, it turns out, is about 2.2 eV, so that's plenty high enough. So if I had a band gap of 2.2 eV, let's say 2 eV, so 1.24 divided by 2, that would be about 0.6. So that would normally have given you an emission in the orange or maybe green, depending on the gallium. Yeah, maybe green, okay? The problem, however, is the following. Okay, so if you look at the band gap of this gallium arsenide phosphide system, as I add more and more phosphorus content, X, to the system, okay, this shows what happens to the band minima in the conduction band, okay? Probably need to refresh your memory about this nomenclature. So if you look at the EK diagram, that's my valence band at K equal to 0. Conduction band, if it's at K equal to 0, that is known in shorthand as a gamma point. The minimum along the X direction, now this is not this X. X direction means the 1, 0, 0 Miller index direction, okay? That's known as the X minimum. And along the 1, 1, 1 direction, if I have a minimum there, that's known as your L minimum, okay? So what you find is for gallium arsenide, the minimum is at the gamma point, meaning it's a direct band gap semiconductor, right? But as soon as you increase the phosphorus content to about 0.44, notice what happens. These band edges, these L, gamma, and X shift differently, okay? And by the time you go above 0.44, unfortunately, the band structure looks like this. The minimum is no longer at gamma, but the minimum becomes X, okay? And of course, if it's X, is it direct or indirect? Anybody?
Indirect.
Indirect. And as such, the output efficiency, light output would be terrible, right? So people were in a bind. Now, believe it or not, what came to our rescue is our good old Heisenberg uncertainty principle. Now, when I talked about that in chapter 2, some of you probably rolled your eyes secretly and thought, oh gosh, why are you talking about crazy quantum physics like that? What use is that, right? Well, that's used in this particular case. So what they did is add a little bit of nitrogen to gallium arsenide phosphide with a high concentration of phosphorus in it. So, this range. Okay, how does it help? Well, if you look at the periodic table, remember, gallium is in column 3 of the periodic table, and arsenic, phosphorus, and nitrogen, they're all in column 5. Okay? So if I now make an alloy of gallium arsenide phosphide, but then add a little bit of nitrogen to replace some of the phosphorus or arsenic atoms, would that nitrogen act as a donor or an acceptor? This is a trick question, so think carefully before you answer. I'm replacing either the phosphorus or the arsenic with the nitrogen, so-called isoelectronic impurity. Is it a donor or an acceptor?
Should be a donor, but if it's a trick question, I guess it's an acceptor.
It's neither. For something to act as a donor, the impurity has to have one more electron in the valence shell than the host atom, right? To act as an acceptor, it has to have one fewer electron. Since nitrogen, phosphorus, and arsenic are all in column 5, that's why it's called isoelectronic. It's neither a donor or an acceptor, okay? It just sits in the lattice and forms a deep potential well. Not necessarily deep, but a narrow potential well like this, okay? So if I put in the nitrogen in the lattice, it forms a potential well like this. But the physical extent of this delta X is very, very small, okay? That's where Mr. Heisenberg comes in. What does Heisenberg tell us? Delta K times delta X is of the order of 1, right? Greater than or equal to 1, right? So if I have a nitrogen defect, which is tightly confined in real space, and if I look at the corresponding defect state in K space, which is the so-called momentum space, delta K is going to be very, very large, right? So by adding a little bit of nitrogen to the system, I get a defect state due to the nitrogen below the X minimum, but that has a large delta K. So now electron falls into the nitrogen level. It doesn't know what the momentum of that electron is. It rattles around. Now it's able to recombine very effectively and give off light, okay? And that's how people got red LEDs and orange LEDs, okay? And subsequently with other alloys, green, okay? So if you're old like me, when I was in school, my first calculators were with a red LED display, not because industry loved the color red, but simply because they could make use of the Heisenberg uncertainty principle and gallium arsenide phosphide diodes doped with a little bit of isoelectronic nitrogen. All right. Now, so pretty early on, people are able to get red LEDs, and then with a little bit of tweaking, they're able to get yellow and green. But try as they might, there's nothing available in the blue part of the spectrum, okay? Because for blue, you need much larger band gaps, as I pointed out, right? You need something of the order of, 3 electron volts or so, all right? And the gallium arsenide phosphide system gallium arsenide is over here, phosphide, it simply couldn't get up there. Okay, so that the whole field of LEDs kind of, you know, hit a kind of a dead end, if you will, because try as people might, people could not get high enough material quality in the high band gap system, the so-called gallium nitride based systems, indium gallium nitride or aluminum gallium nitride and things like that. Okay, until in the late 90s, early 2000s, a group in Japan, they're called Shuji Nakamura and his colleagues, were able to grow high quality nitride semiconductors and alloys, things like indium, gallium nitride, etc., etc. And these have much larger band gaps. It's not shown on this figure. I mean, they have band gaps in the 3 to 5 EV range over here. Okay, so by improving the material quality, you're now able to make blue and violet and even ultraviolet. Not only that, for some very interesting reasons, even though these semiconductors, these nitride semiconductors, are actually not very defect free, they have a lot of dislocation type defects in them. For some reason, Mother Nature was kind to us. She decided that these defects wouldn't impede the optical output efficiency. Normally, if you have defects, it's sort of the kiss of death for light output, because the defects can cause energy states in the band gap and give rise to non-radiative recombination. Okay, but luckily this one turned out to be a forgiving system. So finally, people were able to get red, green, and blue. Now, what do you get if you combine those three colors? Well, those are the three primary colors of the spectrum, of course, and you get white light, and you can get bright white light. Okay, and that, as I'm sure you know by now, if you ever visited Home Depot or Lowe's or gone to Amazon, you can now buy these very, very high intensity LED light bulbs, which are much more efficient than your old tungsten halogen light bulbs. Okay, if you think back a couple of decades, if you look at these tungsten halogen light bulbs and you feel them with your hand, it's super hot, of course, because 80 to 90% of the electrical energy input is wasted as heat. On the other hand, if you feel an LED light bulb, it's cool to the touch, right? Because it's got very, very high efficiency. I mean, 90% plus of the electrical energy input is emitted as visible light and very little wastage as heat. That's one beautiful thing. Another nice thing is the reliability of these light bulbs is very, very impressive. The old tungsten halogen light bulbs typically burn up in about 2,000 hours or so, okay, because the filament oxidizes and burns up. These LED light bulbs by themselves have projected lifetimes of 100,000 hours. Now, in practice, they don't really quite last as long because the LED itself survives, but the electrical connections, that tends to fail in some cases. So they're not quite as good as 100,000 hours, but still much, much more reliable. They have much longer lifetimes than old tungsten halogen light bulbs. Okay, that of course creates an interesting economic challenge for these companies because they can't sell these quite as often, but they charge you an arm and a leg. Now this, of course, because of this high efficiency, is really making a huge dent in this whole global energy consumption and hopefully global warming. Is question? Was there a question? Okay. Now, the basic physics of the LED is not that difficult, but there's a lot of details that I haven't gotten into. So this is a very interesting chart. Not really much science, but this shows the first Thomas Edison light bulb around, I believe, 1900. So it's not on the scale, okay? So this is light output efficiency in lumens of light per watt of electrical energy as a function of time, okay? The first LEDs, as I said, were made in gallium arsenide phosphide with this nitrogen isoelectronic doping. This was done by one of my professors at Illinois when I went to grad school, Nikoloniak, but not very efficient, okay? If you're weaker than the tungsten halogen light bulbs. So then over time, with nitrogen doping, they got it brighter and they're able to get green and yellow. But they couldn't get blue until the 90s when this group in Japan finally were able to get the nitride-based semiconductors and made blue, and then you could combine them. And notice how the efficiency also improves. So now LED light bulbs are not only more efficient than and more intense output than incandescent light bulbs, but also fluorescent light bulbs. Okay. Now, some of the technology that I haven't talked about is you have to be careful when you design these structures. So if that's my PN junction diode, say, suppose I have electrical contact over here, then I have electrical contact at the edges, I forward bias the thing, you have recombination of the electron hole pairs, and light comes out, okay? But when the light comes out, suppose that light hits the surface in this direction. Well, remember, this is a semiconductor. Well, outside I have air, but the refractive index equals 1, but here the refractive index is much larger, okay? It's of the order of whatever the square root of the dielectric constant is, okay? Now, if I go from high refractive index medium to low refractive index medium, what happens? The light will tend to refract like that. And if this angle of incidence is greater than the critical angle, it will undergo total internal reflection, right? Which will be a shame because I'm generating light within the structure, but I simply can't get it out of it, right? So to solve that problem, typically these have nanostructures put on top of them. You have these convex lenses that are formed out of glass. Okay, so now when the light hits it, even at glancing angles, you know, you're not above the critical angle, and you can get the light output out of it. Okay? And then there's engineering issues about how you combine multiple LED light bulbs in what are called luminaires to get LED out of it. This final slide is really just for fun. So if you ever get on, this shows you can get light out of semiconductors or solids by exciting them in multiple ways. So you can absorb photons, and the electron hole pairs can recombine, give off light. That's called photoluminescence. For LEDs, of course, you want electro luminescence, okay, which is where is it? Yeah, electroluminescence. So that's what I've been talking about, okay, in an LED or a laser. But there's other sources of energy excitation which also give light. And one thing that I read that was very interesting was you can convert mechanical energy into light, okay? And that's called triboluminescence. So you can take a piece of semiconductor in a dark room, and if you shatter the thing, if you break it, you'll see a spark of light coming off from it. So you can do that experiment at some time, okay? So you can take a piece of gallium arsenide, shatter the thing in a very dark room, and if you look carefully, you'll see light coming out of it. You're converting mechanical energy into light output. So if you ever get on semiconductor jeopardy, this should be useful to you. So that's all that I have for the course. Very briefly, I want to tell you about lasers. That's not part of the course. So a laser, like I said, is a cousin of an LED, but in a laser, you take a PN junction and you have to bias it very, very strongly forward biased, okay? Bias it very, very strongly forward biased, okay? So that you inject, see, that's my P side, that's my, so I'm injecting holes this way and electrons this way, okay? I inject so many electron hole pairs that you get something called population inversion. This is just for fun, you're not responsible for this in the exam, okay? What does that mean? Well, normally, if you look at carrier occupancy as a function of energy, we see that higher the energy, the occupancy factor tends to go down, right? Typically, in classical physics, that's the so-called Boltzmann factor, e to the power minus E over KT. So higher energy states will have lower occupancy than lower energy states. Well, in a laser, you drive it so hard that it can actually have temporarily more carriers at a higher energy than at a lower energy, okay? And then those electron hole pairs recombine and give off light, kind of like in an LED. But the difference now is when the light is emitted, it's confined within partially reflecting mirrors. So at either end, you'll have partially reflecting mirrors, okay? So the photons that are emitted under population inversion conditions reflect back and forth. Now it's only partially reflecting because ultimately you want the light to come out at one end, of course, out of these so-called edges in this edge emitting lasers, okay? So the other part of the physics is physics developed by our good friend Albert Einstein. So Einstein in the 1920s had looked at this problem. He didn't know about lasers. I mean, lasers hadn't been invented then, but he proposed, based on basic statistical physics, that light emission has two components to it. The one that we've been talking about so far is called spontaneous emission. Okay, so from a high energy state, electrons fall into the lower energy state, and up photons come out. But on top of that, Einstein said that you could also have a so-called stimulated emission component. Okay, and these are given by the so-called Einstein coefficients A for spontaneous and stimulated coefficient B. Okay, where the stimulated coefficient is light output, which is triggered by the photons themselves. So when a photon goes back and forth, okay, that induces additional electrons to recombine and give off more photons. And for the stimulated emission part of it, these photons that come out don't come off in random phases, okay? They all come out in lockstep, okay? The coherent radiation, okay? And because they come out in lockstep, that's what a laser is. So when you have light output of a laser, because all these photons that are coming out are in phase, this beam doesn't diverge. You have a highly focused beam, okay? So that was, the analogy that I was telling you last time. So this is like, ROTC students at Texas A&M coming out of class all in phase, or, soldiers marching out of a classroom in phase, versus a random mob, going out in all possible directions. So that's what a laser is. It's a very, very important device, very, very interesting, a lot of physics to it, which obviously we haven't covered at all. But if you, get interested in the field, there's follow-on courses taught by Professor Seth Bang on lasers, Professor Dudha Balapur on solar cells, and then, so there's more advanced courses on all of these topics, okay? I think I'm done. A few words about the final exam. So the final exam, like I told you, will be through Canvas and Zoom. I'll be posting the final exam under Canvas, under files, where all the homeworks are posted, and they'll be available to you about 15 minutes before the start time of the exam. I told you what the exam dates are, okay? So if you want to print it out, you can, but you don't necessarily have to. You can just look at it on the screen. Once you solve them, you need to turn them in after the 3 hours as one single scanned document under assignments. The TA already put up a link in there. Okay? It's important that you don't have multiple files, otherwise apparently the system gets confused. So you have to combine them into one scanned PDF document, and you have to submit them under assignments. Let's see. For the exam, I have not given you any problems from chapters 1 and 2, so you don't need to review that, okay? The most important ones are chapters 5, PN junctions, and chapter 6, MOSFETs. Now, 3 and 4, which is drift diffusion theory and carrier continuity equation, unfortunately, you do have to review, because, and if you think about it, it's really applications of those principles to different devices. So although I won't have problems specifically from chapters 3 and 4, you still do have to review that, because it's applications of that to 5 and 6. I've given one problem on BJTs, but for the BJTs, you only need to focus on the first part, which is these concepts of DC transport and base transport factor, emitter injection efficiency, and current gain, and things like that. Okay, you don't have to worry about the more complicated Ebers-Moll model, transient behavior, etc., etc. Okay, study heterojunctions. I have given you a problem on heterojunction band diagrams, etc., etc. Okay, that's a very important concept. And then the optoelectronic devices, I've given you one short, not really a numerical problem, but so typically in the exams, I would have given you a few essay type problems, but since this is open book, open notes, I can't really do that. So I've won multi-part short problems, which are not really quantitative, but thought problems, if you will, okay? See, what else? Make sure that you fill in the evaluation forms. You should have gotten an electronic request. What else? Well, let me throw it open for questions. And then, if you have any questions between now and the final exam, by all means, shoot me an email and I'll try to respond promptly. Okay? Because it's been such a weird semester, I'll be more generous than usual with the grading. So you don't have to panic, unless you've blown off the homeworks completely, or you can't answer anything at all in the finals. I'll not flunk you. Okay, so it'll be mostly A's and B's and maybe a few C's. Okay, so you don't have to panic too much. But please do study, of course. With that, I'll take any questions.
Just out of curiosity, like as someone who's going into the nano manufacturing field or nano electronics and stuff like that, is it worth it in undergrad to devote like time in your degree plan towards graduate classes, or just to take like more upper division undergrad classes?
So for getting into good graduate schools, the GPA matters a lot. Okay. So when I look at candidates, that's the most important thing I look at, and the quality of the school, right? So, a 3.5 from UT is valued much more highly than 3.9 from a no-name school, right? Like A&M. That was a joke. Don't think A&M is an absolutely wonderful school, right? So what I was trying to say is, if you end up taking difficult grad courses and messing up your GPA, that's going to hurt you, right? Having said that, a lot of undergrads in the solid state track who want to go on to grad school do take the follow-on device course taught by Jack Lee. It's sort of 339 enhanced, if you will, right? And that's something that students can handle quite well if you're interested, okay? But I would not take Frank Register's course, for example, because I think it might be too hard. And then if you mess up the grades, that's going to hurt you more. So you get some credit for taking grad level courses, but then if you end up getting C's, it's really going to hurt you. So mostly focus on the undergrad courses and focus on trying to get good grades, okay?
So the exam is May 18th at 2 o'clock, is that right?
Whatever I sent you, yeah. I believe that's right, yeah.
Also,
yeah.
So considering if someone being interested in nano electronics, does it matter if we wait to take if we just take the 440 class next semester with the other professor, or wait to take it with you after that?
No, you can take it. The other professor is wonderful. Praveen, yeah, he's much better professor than I am. So by all means, if you have time, take it next time. Yeah.
All right.
Okay, anything else? All right, good luck. You'll do fine. Like I said, I'll be gentle with the grading, but don't blow off the course completely though, right? Good luck.
Take care, Professor.